Okay, let's get going. So it's almost the last. This is the last lecture. On Tuesday, we will have final exam review. It's essentially we'll try to solve some questions from previous exams, and just in general, maybe talk about how things work in X6. Right, mostly covering the second part of the class. But feel free to come and ask any questions about the entire class on Tuesday. So we assigned finally the very last homework, but we made it an extra credit. So because of how late we are with it, so we said, okay, it's probably unfair to ask you all to complete it, but I think it's like 5% of your total class grade. So roughly speaking, if you do the homework and you're at 80, it will give you 85, which might move you between grades. And it's not a hard homework. It's about file systems. So like literally, if you carefully follow it, the class, then it will take you like less than a day to finish. I mean, day meaning several hours. I think that's the news. I don't have anything else. So any other questions about logistics? So final, same format as midterm. We'll touch, like people pointed out, a couple of vulnerabilities on the midterm, and then we will try to implement measures to make sure that they are not exploitable during the final. Anyway, so back to synchronization. So we have a couple of people on Zoom today because they asked, because of the rain, they were not able to make it, but sure. So, okay, so what we were doing last time, we were talking about like essentially the idea that really the machines which we use, they are those distributed systems which with multiple processors, physical like pieces of hardware, and each processor comes with a bunch of cores, like numbers like whatever, like 56 threads are not uncommon today. So the recent Intels like happily will sell you stuff like that. And obviously everything what you're gonna use in production will be this multi-core system, right? And like again, this is the drawing of a typical modern server. Everything is distributed, right? We have memories attached to like through a memory controller to a specific processor. So if you have multiple processors, most likely we'll have memories attached locally to them, similar for PCI devices here. And essentially there will be some kind of a link between them, like we can call it a cross-socket link because people typically call this a socket. And as we were saying last time, all communication is in terms of cache lines. So if you essentially fetch even a byte from memory, in practice 64 bytes are fetched. This unit is called a cache line. And there is a protocol which implements at a high level, implements an idea of concurrent readers, exclusive writers. So essentially this cache line can be like cached and accessed in a shared state on multiple cores, and then multiple cores can read it in this shared state at the same time. For example, if you like spinning on a loop, checking for some condition to change, and then one of the cores tries to store into this cache line. When the store is issued, the system works as following. It invalidates this cached cache lines on all the cores, moving them into invalid state, and like essentially fetch the cache line in the exclusive state, meaning that only this core has this cache line in the exclusive state, so it can perform a store. And those guys who loop on this cache on the same cache line, since it's currently in the invalid state, will again issue requests to this core. This core transitions from exclusive. It depends on the protocol, but we can say it transitions to shared, and then this guy get this cache line again in a shared state and can keep reading it, right? So the idea of bouncing the cache line should be kind of in your head, and it explains a lot of like weird stuff which can happen. So, and just to like warm it up a little, if I ask you a question, like if I have an inc instruction, which is an increment, and I increment something in memory, EAX, like it's an address pointed by the value of EAX. Is this increment atomic or not? What do you think? Well, why not?
That's a read-dependent operation on the.
Correct. So it's a little bit hard to understand because you think, okay, inc should be like an atomic operation, but in practice, the CPU, and I mean, I don't know the details, but I agree with you with what you said. CPU translates it into 3 different operations internally: load of this value from memory into some internal register, let's call it R1, for example, doing an increment on a register R1, right? Sure. Like that's atomic on a register, and then a store back to memory of this whatever, depending on what syntax you choose, back into memory. And like again, the way to think about it is that like if this load fetches a cache line, it can lose it because, or it can try to fetch a cache line, do an increment, but before storing it, it loses the ownership of a cache line because some other core says, okay, request for ownership, like fetches the cache line, modifies it, it's an old value, it's like incremented here, for example, then the store fetches it back and obviously overwrites it with this value, but we lost one increment, right? So any operation which can be thought of like as multiple micro operations will not be atomic. And it's the same for this instruction, which we looked at, exchange, right? It's the same idea because it's a load and then store, right? And you can lose atomicity here. And so what Intel is doing, they implement this lock prefix. If you put it in front of an instruction, what it means, it's kind of like locks this cache line. So if you have this lock prefix and you loaded the cache line, and even this request for ownership comes to like local L1, L1 says, okay, hold on, this cache line is locked. I will not release it for a while. I'll finish this operations and then release it, right? That's kind of the explanation of what's going on internally, right? Make sense? So, okay, yeah, so those lock prefixes are important. We kind of understand how they work. And what we were doing last time, essentially where we left, we were talking about this example where it's a list, it's updated from multiple cores. We agreed that, okay, that's not okay because we might lose elements on a list, like that was our discussion here, this element is lost. We implemented idea of critical section, so essentially a sequence of code which executes exclusively by one core at a time. And this lock or this list lock enforces the fact that if one processor already executes inside the critical section, other CPUs will be waiting, trying to acquire this lock, right? And then we started talking about, okay, what's going on, how to build this lock. And essentially we agreed that these 2 checks are not atomic because you check for the value and then write it. That's not okay because you may lose the cache line here in between. And essentially we came with this idea that we will use exchange instruction with an atomic lock prefix, right? And I lost power at about this time, but essentially the idea was like what prevents the CPU from reordering instructions, like moving any instruction after the lock. So either in this exchange function or from the critical section, because we all know that CPUs are out of order. So okay, if there is no dependency between instructions, and specifically in this case, there will be no dependencies between this instruction and instructions inside the list lock because it's just a different variable. So CPU potentially can move them outside and execute them out of order. But the convention on Intel is that Intel does not reorder instructions around the atomic lock prefixes, right? Because they're guessing that there is some kind of a synchronization primitive is going on, and so it's probably not okay to do this. But there are CPUs in which it's not the case, and they use an explicit barrier which instructs the CPU to say, do not reorder instructions. The same kind of applies to a compiler, because imagine that this acquire function is heavily inlined, and compilers do the same transformations. They say, okay, there is no dependency between those instructions, and essentially compiler might choose to move those outside of the critical section, right? And so, like, there is this trick which MIT people are using. They say they give compiler a hint it's a hint to the compiler. It doesn't mean anything. It doesn't translate to anything. It just hints the compiler that it should not reorder instructions. I think, again, I'm not an expert in compilers, so maybe go talk to John Regier or Pavel. They will tell you what's going on currently, but I think modern compilers like GCC LLVM, they also do not reorder around atomic instructions. It's kind of the same idea. So I don't think I ever seen this line in practice, although I can be wrong, right? But just keep that in mind, that there are like two levels: out of order CPU and essentially a compiler which can also reorder. And so again, you can tell me, okay, why does it matter? So like, who cares? If you get into this area and start building those synchronization primitives, sometimes you can build them without atomic instructions. That's kind of, you think it's unbelievable, but it's doable, and you can use the properties of this. Remember this cache coherence protocol, which essentially governs how the cache lines are moved between the cores. There is a discipline which is called consistency, and essentially it's how the writes are ordered. And you can use this, like, you can use this discipline to essentially say, look, I don't need a lock in a specific case. And then watch out. So because CPU might not understand, most likely will not understand that you're doing something like that. And then you have to be careful with those barriers, even on Intel. And maybe even the compiler might do something weird for you. So like, just be careful. But okay, so we got the basics of this acquire release, right? So essentially atomic exchange instruction, it returns the old value. If you see that the old value was 0, you move into the critical section. If it's still 1, you keep spinning. Release is just a simple write because it doesn't need to be, it's already atomic, right? So you don't have to do anything. Any questions about spin locks? And we will move on forward, explaining what the problems might be with them. Okay, cool. So then there's a couple of problems, obviously, with using the synchronization primitives, and you have to be careful. So an obvious problem is this. So a deadlock. Imagine you acquire a lock. Imagine on the code path, you really have to acquire 2 locks. So you first acquire A, then you go forward and you acquire B. And sure, why not? Everything works. But what if some other part of your code, like which executes on a different CPU, somehow acquires B first, right? And essentially, at this point, you say you already acquired A, you're waiting on B, and this guy acquires B first and then waiting on A. So, and at this point, you end up with a deadlock. Those guys will be waiting forever because they will never make any progress. You see a problem? So how to fix this problem? What's the natural solution? We'll get to it in a second, but nothing really, like, even if you disable interrupts here. So that's a good question, actually. Imagine we do int disable before acquiring the lock. Disabling the interrupt, why this question is important, only affects this one local CPU, because disabling interrupt changes E flags. And E flags is just a register on this core. So the other core can move in, also try to enable interrupts, but the same happens. Even if you do int disable on the other core, you still go and acquire B, and then all still go and end up with a deadlock. That's also a good question. So, like, obviously, these locks A and B, they are shared, right? So both A and B sit in the same cache line. So it just that this contains like locked for A, and some other cache line will be containing locked for B lock, right? But obviously that's the same address in memory. I mean, it can be different virtual addresses, but it's the same physical address, and they like move between the cores back and forth. You can say, look, I give up. I don't know the solution. So you say, look, instead of 2 locks, I will be just using 1, and I will be acquire 1 big lock when I, for example, enter the kernel and say, look, and I will execute everything under this lock. And that's a solution. I agree. So this problem disappears, right? The reason they use 2 locks here, or in this example, or in general, why you use multiple locks, is to implement fine-grained locking, right? Because if you acquire 1 giant lock, the entire data structure is locked. Imagine you have a giant hash table. If it's under 1 lock, only 1 core at a time can access the entire hash table. But naturally, hash tables, because of the hashing function, you will be landing on all over the place on a hash table. There is no conflict in most cases, right? And so you say, like, maybe one big lock is not a good idea, right? Although again, I appreciate the kind of the thread of this discussion because it allows me to explain the fine-grained locks. You had an idea?
Okay.
But how? Like, what's your refactoring discipline?
I don't know if it would work in this case to acquire, like, just swap the order for lots and just acquire A and B, acquire B.
Well,
Side maybe.
Right, and that's the answer, kind of. Although maybe it's in between the lines, but the solution is you need to acquire locks in the same order, right? Always. Then it guarantees that you not end up in a deadlock, right? You think, okay, that's easy, trivial. But imagine you have not just like static, like file system. You first acquire the lock on the process tree, then on a file system. That's trivial, but still you have to keep it in mind. But which gets kind of a little harder in a real kernel. And Linux has a bunch of those like problems with locking because it's so scalable. But also imagine you have some kind of a graph data structure, and the goal of your code is to walk this graph. And you say, look, I really want to modify, like, my transaction touches like 5 nodes of this graph. And I say, like, I have to acquire them all or in some order. And some other transaction, surprise, comes into this graph. So this transaction 1, transaction 2 comes from a different node. Maybe it's a list of pages in the system, and you somehow like say, okay, I want to modify them all. And you say, like, even maybe a subset of this, it's only a subset of these nodes, right? Because you say this transaction touches 1, 2, 3, and this touches only 4 and 3. Now what we do? How do we solve this problem? Because at this point, it's not like lock type A, lock type B. Those are just instances of the same type. I don't know, let's say pages. How do you solve this problem? You don't know upfront the order, right? So what do you do now? You do, like you say, I have to take a look on 1, on 2, on 3 for this transaction. And this T2 says, okay, I'm entering from 4 points to 3. So I clearly have to, like, you don't know, like, you know that you start from 4, then you might acquire 3, but you might deadlock because if this one goes into, like, maybe this one goes something like 1, 2, the fact that I have only 1 here probably makes it a problem, but maybe this one goes, let me change it. The color, so this one goes like 1, 2. So they overlap on multiple, and if you acquire them out of order, you still deadlock.
Guarantee to sleep for a while. Like,
no, but the problem of it was the sleep. No, okay, it's also a strategy. So imagine T1 says, okay, I want to acquire 1, 2, then 4, then 3. And imagine T2 enters it from a different angle and says, okay, I first acquired 3, and then I'm trying to acquire 4, but 4 is already acquired by T1. At this point, you say, no matter how long I will sleep, the T1 will not make progress because it's waiting on 3, right? No, okay, like, okay, we have a queue. So T1 says, okay, I will acquire 1, then 2, then 4, then 3. T2 says I will acquire 3 and then 4, and they kind of like, they deadlock on 4, right? Because this one cannot move to 3, and this one cannot move from 3 to 4, right? Well, they have, oh, you want to implement like global, essentially what you're saying, you always have this big lock in your head and you say, look, no. They will have priority and only one of them will acquire locks at a time, not concurrently, which means that we are back to big log, right? It looks to me, maybe there is a solution. But what other solutions do we see?
I'm just wondering if you didn't watch this case, like your graph on
That's a good approach. So if you say that my application domain allows me to do that, never hold multiple locks. That's a good approach, and it also improves granularity. But what if it's a transaction and really like you want to somehow atomically update 4 of them? Then it's not an option. And I mean, it doesn't arise very, very often in systems, but in other code, it does happen. In kernels, it's not a very quick, I mean, like again, like kernels are like semantically reasonably simple that I don't even have an example of this graph, but just wanted to make sure that we'll all understand. But the solution very easy. Like, I mean, first of all, there are multiple solutions, and if you wanna learn about all of them, go take a class from Ryan Statsman, distributed systems. He will tell all about locking and like multi-phase locking and stuff. But in systems, we solve this problem in exactly the same manner. In systems, you know, people are like lazy. The lazy solution is to say, look, first figure out which locks I have to acquire, 1, 2, 4, 3, and then make sure that you sort them. And you say, look, I know that I have these ones, and I will acquire them in ascending order, 1, 2, 3, 4. And if this guy does the same, then locks are acquired in the same order, so there will be no deadlock. And so, like, how do you sort something? You can, for example, use the addresses of those objects and just sort on an address. But that's one efficient, like, pragmatic solution to do it. There are more complicated solutions where you say, look, if I cannot acquire a lock, like you say, for some amount of time, we will backtrack and release some locks and try to reacquire them again later. That's also a solution, but it's more complicated. But sorting and acquiring locks in the same order works reasonably well. And I don't want to go into the discussion when it doesn't, like, when it's from the performance standpoint, it's not ideal. Again, go listen to Ryan Statsman. He's an expert. Okay, that makes sense? Answers the problem. It's same idea. Lock, acquire locks and lock in the same order. It's just that not always it's like A and B, and you can like statically kind of verify that you do it. Sometimes it's all dynamic, and you'll have to sort the instances. But still, again, if you write kernel code, and sometimes you have to acquire multiple locks, like file system, processes, like, I don't know, inodes, buffer cache, something else, maybe blocks, like at least make sure that you, I mean, like you say, either you hold one lock at a time, it's not always possible, but then you need to make sure that you always acquire them in the same order. So even if you enter the graph and you say, look, I only have to acquire inodes in a buffer, just make sure that you do that and it like matches the order throughout the system. Here's another problem, which is more like it doesn't exist at user level to a large degree unless you process signals or something, but that's related to locks and interrupts. Imagine we have a network driver in a kernel, and a network driver maybe adds packets to the network queue. I always will run out of some kind of power. Okay. So here you say you enter the network packet function, you acquire a lock, and then suddenly an interrupt comes in. Maybe it's even on the same core. And you say, look, hold on, network interrupt. I mean, I need to like again fetch a packet from a network queue, go into the same insert function, and I will try to acquire the same lock. And of course, there is like this line of a deadlock between the same log. So how can we solve this problem? Tell this again. So, okay. I didn't quite got the answer. So maybe someone else can rephrase it for me, or maybe you. No, but hold on. It's the same interrupt. It like vector some number, and you just get it twice. You of course can say, what can you do at this point? So it's the same network interrupt, same priority. And again, it's kind of a simple solution. Again, in systems, a lot of stuff is simple. But
This, your earlier suggestion of disable interrupts when you're handling an interrupt.
no, kind of, almost. It's like, it's what? When you acquire a lock, exactly. So the answer is like never acquire a lock with interrupts enabled, because wow, it can happen that another interrupt will preempt you, unless you somehow know that, okay, this interrupt processing code will never touch this lock again, right? So, and this is what x86 is doing. So when you enter acquire, they disable interrupts. And of course, you cannot just disable interrupts and re-enable them simply, because if you have two nested locks, right? So you disable it once, you disable it twice, but the moment you release the second lock, you're re-enabling the interrupt, right? So if you have the nesting, you have to keep track of how many times you already disable the interrupt, right? So they maintain a counter, meaning that, okay, every time we disable an interrupt with this push CLI, we increment the counter, and every time we pop CLI, we decrement the counter. And only when we reach zero again, we re-enable the interrupts, because at this point we know that we don't have any locks. We don't hold any locks, right? Make sense? So in systems, so that's why it's hidden here in push CLI, but it's again, this is the solution to do this. So this is pop CLI. So it's essentially says if this is like negative, then panic. This is panic, but if it reaches zero, then you by the way, it had interrupts enabled before, then you re-enable the interrupts after that, right? Because maybe there was a case that the interrupts were disabled to begin with, and you keep track of it as well. So now you finally know those final fields in the CPU data structure, right? And it's a per CPU interrupt. Obviously, acquiring and releasing an interrupts, it's all like private to cores, right? So essentially each core will have its own E-flags. And the fact that you disable the interrupts here will not affect this CPU, right? Okay, good. We got this. Okay, sure. Now let's talk about how we can implement this, or what kind of problems might happen when we do synchronization across multiple processes, right? And I will first use a simple example, and then we will take a look at the implementation of a pipe in x86. So I kind of early this semester, I promised that we'll get to pipes. So today is the day. So first, very simple example. So it's a send receive queue. Like it's a very, very artificial, simple example, but to make it real, the queue will be like sending multiple elements. But here we have just one pointer. So literally, it's not a queue. It's just like queue is one element. And you say, you want to send your send primitive takes an object like a void type, which it will say, look, I will assign to this queue pointer, and it means that I send this object to the receiver, right? So receiver here says, okay, good, like I will, like essentially I will wait for until this pointer shows up. While it's zero, I will be spinning. But the moment it's not zero, I got the pointer P, and I will like return this P essentially. That's a way to send this object A. For example, this might be one process, this might be another process, and they just say, okay, I will send you an object. I will send you a pointer to an object, right? So the send operation is kind of simple. You say, look, I will have a pointer to the Q, and a pointer to the object P. If the queue is not empty, it means that an object is already queued for receive, so I'm not gonna kick it out of the queue. I will be waiting for it. The moment it got received and like reset to 0 here, I will queue this P on the queue, right? Makes sense? That's a send. And received is similar. You say, I have a pointer to the queue. I want to receive a pointer to the object. You will be waiting in a spin loop for until this pointer is not 0. The moment there is something, you get it, assign it to P, and reset the queue to 0 so you can send again, right? And you're returning this P, right? Make sense? Any questions about how it works? Okay, let me ask you a question. So my wonderful poll time, and we will ask the question. My question is, like, what statement describes this queue the best? I give you like a couple of options. And I will leave it on the screen so you can look at the logic of this queue. Is it on? Not yet? Okay, sorry. On now. The only problem I have is that I don't see how many answers I received. Be nice to have it. Also, I don't have my mouse pointer in, but why? Just kicked out my mouse pointer. So right now, people are split between the option number 1 and option number 3. So who can tell me which one is right? What's going on with this queue? Anyone who votes for deadlock, option number 1? No one in the class? No one wants to explain why deadlock can happen. Well, okay, like give me an option which you guys like. Anyone? Yeah, you're saying so it actually it looks like it works, right? But it just wastes a ton of cycles. And why do you think so? It kind of like there is not even a single atomic operation. This is the case which I was describing, that you actually rely on the properties of the cache coherence protocol and everything. That, like you say, look, I will be waiting for this pointer to become non-zero, and I will put a pointer, right? But maybe it will be spinning here forever. Not forever, but like maybe you have a long queue of processes. Maybe you're running like 100 processes in the system. Each takes like 10 milliseconds, for example. Multiply by 100, you will get, what do you get, a second, right? For this process, which was not scheduled, to get back to this primitive receive and essentially enter the queue, immediately pop a pointer and just unblock the queue, right? You see the problem. So if you have a lot of stuff running in a system, this guy will just waste 1 sec. In practice, of course, it will not waste 1 second, because if it's equal priority, it will spin for 10 milliseconds and then will be preempted with a timer interrupt, and some other stuff will run, and eventually it will get there. But still, you can waste on average half of this 10 millisecond slice, right? Okay, I agree with this. So it's perfectly fine, but ideally, seem to waste a fair amount of time spinning here. So what will be a solution here? How would one try to solve this or implement this queue in a better way, in such a way that we don't waste cycles or do some useful work instead? Yeah, so sleep is a natural answer. So you say, look, I want to do this check once, and if it's empty, I will go to sleep here, right? And then I rely on the fact that somewhere here, when this guy pops something up, they will wake me up. We didn't talk about sleep and wake up, but this is kind of the time to talk about it. Okay, sure. So let's try to build it. So we want these two primitives, right? So, and somehow you guess them already, maybe you saw them in the code, but sleep says, okay, what do you actually want sleep to do? I will ask you. No, but internally, like if I ask you add sleep to x with 6, what will you put inside this function? No, like in what? No, but maybe not even, don't give me the details. Just what's the intuition? What do you want to happen to the process which is running currently?
You would want to basically scheduler store something internally to schedule and to pop back to it when
Correct. So what we want to do, we want to yield the CPU. We have this function yield. Internally, yield will call the switch, like which in x86 switches to the scheduler. But essentially, we say instead of spinning here on this while loop, we want to give up the CPU to some other process and like let it run instead of like spinning for 10 milliseconds, right? And you're right. You say we want to remember a little bit to make sure that when someone wakes us up, they really find us and like switch back to us and stuff like that. Okay, let's take a look. Like first, intuitively, the way like it works in x86 is that sleep passes just a number, a channel, and essentially wake up. Like there will be a queue of everyone who is sleeping on a channel, and wake up just wakes up everyone who is sleeping on a channel, and the sleeping and a wake up is just a very simple thing in x86. They say instead of having the process in a runnable state, it will be in a sleeping state. And so the scheduler will just be skipping over it until it wakes up, until it's woken up, right? And then when someone wakes up, it just says, okay, who is sleeping on this channel? Oh, 5 processes. Let's change their state from sleeping to runnable, right? And then they are schedulable again. Make sense? It's kind of simple. Okay, cool. But imagine we have those functions. I will talk about how to build them later. But, and we probably want to do something like this. I don't know, like say we maybe just for simplicity, just one pair of sleep and wake up. Maybe this guy comes in first. It checks that the pointer is 0. There's nothing to receive. Instead of spinning here, it goes to sleep, right? It passes this number. It can be an address of a queue. Why not? So, and then fine. And this guy, when it comes in, it sends, okay, I put a pointer, I will wake up whoever is sleeping on the same queue, right? Question. Yeah. So you will need to put something like sleep as well. I just want to simplify the example and just consider this one pair. But really, you will put some kind of a sleep here as well, sleep on a queue, and then you will put something like a wake up over on a queue here. But just forget about it. Just it will complicate the reason. So just concentrate on this one pair of wake up and sleep, right? Okay, sure. So we get the intuition how it works. But is it actually works? Does it actually work? So what can be a problem here? That's a problem, but okay, again, go talk to Ryan Stutzman. If something is crossing, the answer in systems is panic. So forget about it. But you're right. That's like next level of things we need to solve. Let's just solve the synchronization problem. Let's imagine nothing is crashing. Well, you already wrote the pointer here, right? So then here you will do the check. You will not go to sleep. You will fetch a pointer. But you're close. You're close to the problem. Think of race conditions again.
Order a little bit so that the receiving process gets the while loop, passes the condition, then the sending process sends wake up, then the receiving process hits sleep.
Correct. And I mean, it's maybe not obvious at the first time, but really it's almost what you said. But imagine this guy does the check, like P1 or whatever, P2 is running, did the check, about to enter sleep. And exactly at this point, this P2 suddenly like speeds up like crazy, turbo boost, like says, okay, wake up, nobody, because nobody is sleeping yet, and exits, but this guy reaches the sleep function and will be sleeping there forever. Moreover, this guy will come back and will start spinning on this loop and will never even like do anything again, right? Make sense? So it's a race. We lost a wake up. So in a book, you will have this diagram, which essentially like shows you like this receiver reaches the test in the loop and about to get to this line, which is sleep, but then sender just quickly stores, wakes up nobody, and this will sleep forever. So kind of the same logic, but presented graphically. So how can we solve this problem? What's the solution? Add logs. Okay, sure. Why not to add logs, right? So I put some logs for you here already just to save time. I will ask you a question again. Does it work? Did we solve the problem? I think it's even, I don't fully agree with you, but let me take another answer. Right, so this is what's happened. So like the problem is like again, let's use this one. You acquire the log, so it's set it to 1, and then you go to sleep, which means that you're sitting on a scheduler queue and will never be scheduled again until you're woken up. This guy reaches this log, but it's already 1, so it will be spinning here forever, right? Not being able to even reach the wake up. Make sense? Okay, that sucks. So what's the solution then? Right, and intuition is correct. So what we say is that, well, we'll do this trick. We'll pass this log, which we acquired here, inside the sleep function. And it will arrange the sleep function in such a manner that it will synchronize the access, maybe acquiring some other log. And this is what happens in reality. And then release this log, right? Meaning that, okay, we know for sure that while this other log is held, nothing will move forward, no wake-ups will be issued, but at least when you will be sleeping, this log will be released. And so someone else can come here and wake up. Make sense? Let's take a look at how this is implemented. So finally, we got the sleep function. So the sleep function like does these 2 steps. It uses the p-table log, and p-table log synchronizes all actions on processes, and specifically sleeps and wakes up. So even if someone tries to, if you acquire this log here, at this point, if someone tries to wake you up, they will be waiting on this log. So wake up is not happening. It's synchronized with this log. At this point, it's safe to release the log which we pass inside. So this one, and just move on and like hear what implement this queue, we just put the number and we set the state to sleeping, right? So the scheduler will be essentially looking at the state, will be skipping over. And I said that it's a queue, it's not really a queue. The scheduler will go through all the processes in a sleeping state when wake up is issued in x86, and we'll compare these two numbers and wake up only those guys. And then you enter the scheduler, essentially, this is your yield function. Here you will switch and so on. There's a little bit of a trickier here, but again, you come out of it in such a manner that you first acquire the p-table log, and then you reacquire this original log to ensure synchronization. So you exit this sleep function with this log acquired again, so this release actually works, right? So it's a little bit like you have to think a little bit twice. And there is an edge case when you actually trying to acquire and release the same log. It's a good edge case as well. So you check here whether it's actually a different log. But okay, so we kind of got how it works. It's not like intuition is there, right? So I explain it a little bit like release. The point is that the moment we release this log, even if the new wake up starts, it cannot proceed because we're holding the p-table log. There is like a couple of other interesting details here. We are holding the p-table log. We are switching to another process, or we're switching to scheduler. The question is like, who will release this log? Who will release the p-table log? Well, the code is written, it's hard to guess, but I mean, it's possible to guess, but the code is written that the scheduler will actually release the p-table log. And the invariant which we have is that we always enter the scheduler with p-table log acquired. It discussed in the book, and you have to carefully read through the x86 code to make sure that you understand it. But the point is that inside the scheduler, like I don't have a slide right now, but this log is acquired, and we essentially make sure that it's released correctly on the way out. Okay, so we solve the lost wake up problem, like specifically wake up. As I said, it's guarded by the p-table log. So you first acquire the p-table log, then you wake up on a channel. Channel is just a number. And literally what this wake up on a channel does, it goes through a list of processes in x86, checks with the state whether the process is sleeping, check if the channel is matching, and then it just switches the state to runnable, and the scheduler will pick this process up and will schedule and run it, right? Okay, any questions about this? Wake up. Good, so let's take a look at pipes. So, I mean, pipes are like glorified, that they are implemented in a way similar to this queue. So essentially what happens here is that, it's back to the homework number, I forgot, maybe even one, shell. So essentially what is a pipe? So in x86, this is the data structure in a kernel. It contains an array of bytes of a pipe size. I think in x86 it's actually 512. And it's carefully guarded by synchronization primitives to make sure that, you know, the operations which you do are atomic, similar to that queue. Let's take a look at how it's done. So essentially there's this lock, and at a high level, the pipe works as a ring buffer. So essentially when you read something from a pipe, these black elements are unconsumed data, which is already added to the pipe. And you read, for example, like, I don't know, here we read 3 elements or 2 elements, right? And so you have a pointer, which is the number of written elements, and you advance the pointer forward by incrementing the counter. And it's modulo 512 arithmetic. So when you reach 512, you go back to 0, right? And similarly, the reads work in a similar manner. When you want to read something, I didn't confuse the read. Oh, okay. So this is adding elements to the pipe. So it's like essentially I should probably mark those as gray and just add the black ones. And reading reads the black ones, but you also have an read pointer, which essentially you advance by the number of elements, how many you read, and essentially they chase each other around this ring buffer. The full condition is this: essentially the right pointer, this one, reaches the read pointer plus the pipe size. And the empty condition is when the essentially read and write pointers are the same, right? Essentially at this point, the pipe is empty, right? Make sense? So it's like, and of course you can push like 1 megabyte of data through the pipe, but obviously there's two processes, P1, which writes into the pipe, and P2, which reads from the pipe. They have to be running and essentially take turns. And this guy can write 512 bytes at a time. This guy can read up to 512s at a time, but they have to, like, the system schedules them on and off, and then eventually you will send the whole megabyte. So that's why if you're building a cell, you have to make sure that you actually let them run versus like waiting for the write to finish into a pipe and then schedule, like start the second one, because then you'll be only limited to like 512 bytes, which you can push through the pipe. Okay, so let's take a look at this pipe read, how it's implemented. So again, you acquire a lock on a pipe, and okay, under some condition, when the process is killed, you're going to release it, right? But essentially, all operations are guarded by this lock. And then you start writing. So you say, look, if you're reading. You say if the buffer is empty, so essentially this condition that read and write are equal, it means that the ring buffer is empty, then you actually will go to sleep here. You say, look, I will, instead of waiting for like a spinning cycles, although you can here, you go into a sleep function and you pass the pointer to this lock into the sleep, so it gets unlocked as we discussed and everything worked correctly. And another important thing here is that the right open end of the pipe is still there, because if this one is closed, then you will never get data again. And at this point, you don't have to go to sleep, but just exit here and say, okay, it's a return, right? Like there will be no more data in the pipe. So that's why it was important to count those open and close for the pipe correctly, because this counter is maintained by the kernel. And unless you close it, you will get stuck here sleeping forever for nothing, right? And similarly, what you do here, so pipe read, just smaller font, you essentially, if you didn't go to the sleep, you have some data in a pipe, you keep spinning here, checking for the condition that the pipe is not empty, because maybe you try to read more than that the pipe has. If it's not empty and you pass the buffer pointer to a buffer here, you just copy in x86, it's just, again, you copy one element at a time, one byte, and you use this modulo 512 arithmetic, modulo pipe size, right? And the moment you're done, like it's, again, back to this queue, and you said, okay, we need to guard both ends of the pipe, you just optimistically wake up everyone. Maybe the writer was waiting for the pipe to become empty because they ran out of space, they want to write more. So at this point, you say, look, I will issue a wake up, and after that, I will release this log. Make sense? So that's like, and not a toyish synchronization primitive, right? So works. And similarly for pipe write, similar idea. So essentially you acquire a lock, you check for whether the pipe is full here. Again, you check for whether the read end is still open, or maybe the process is killed. I'm not discussing the kill condition, but essentially if it's true, then you release and return an error. If not, then you go and wake up the reader saying, okay, I need more data, I'm ready. Or like, go ahead and read some data. Although, like, again, you can maybe skip this step. And then you sleep waiting for the reader to wake up. And you will be woken up here. You will try to attempt this next iteration of this loop and check whether you want to read more data as well. Right. Here you're writing, so essentially, and write pointer, modulo 512 arithmetic, just copying the 1 byte at a time from the buffer passed by the user. At the end, you wake up the reader and you release the lock. Make sense? So again, reasonably simple. So again, just talking here through the conditions. And actually, I think this is it. So I explained this is the end of synchronization, and I can stop right here. Any questions about synchronization? Okay, so since we still have like 20 minutes, we can either end early, but we can also use this time a little. And the way to use this time. So remember, my promise to you is that when we just add a slide here, just an empty slide so I can draw on it. My promise was that I will explain. Where is it? My promise was that by the end of this class, and it's almost the end, you will be able to say something like, I know what happens when you do something like printf, I don't know, standard output, some kind of a file descriptor. You have a like hello. So let's talk through this. So if someone asks you a question, what happens when you execute printf function at user level? Just check our understanding of how operating systems work. How is it done in x86? Just to make, like, just simplify the things a little. Like, you write about the standard library, but in x86, I think it's called utils or something. But you also had anyone, you want to continue? Yeah.
It would basically go and load that into memory and load, start a new process.
What?
Well, actually, no,
Yeah, it will not start a new process.
load in each of the arguments that were in the nick, which in this case would have been printf at the file descriptor as well. Basically, run printf, pick it all, file descriptor, and then
Almost, but can we do a better take on it? What?
One thing that, that's gonna happen is, I think, will write some data to file descriptors and use.
Okay, so yeah, so I agree with that. So we're running in privilege level 3, right? So we're currently in PL3. The kernel PL0. Again, like, I agree, we have a file descriptor table inside the kernel, and the file descriptor table is part of the process data structure, which represents the currently running process, right? How do we get even, like, I mean, this file descriptor points, it's a number, which will be an index into this file descriptor table. How do we get to the kernel? Let's first get through this step. So you were saying that it will load the instructions from printf, but in x86, everything is statically linked. And we can make this assumption, but it's okay. You can say, if it's not statically linked, it's dynamically linked, then we will be using procedure linkage table, lazy linking. Maybe don't go this path unless you really well understand what's going on. I'm okay, but I have to remind myself every time. But just at some point, you should say, look, like, you're right, there will be an invocation of a standard library function, which is printf. And in fact, it's probably this line does this invocation, right? And as you say, those two things like fd and hello will be sitting on a stack as arguments. Like, just mind the order. Fd is at the very top of the stack. Hello is here. It's not entirely true, unfortunately, because printf uses a specific calling convention, which it's not really the one which we covered, because printf allows you to pass arguments of variable size. In my example, it's a static, like, because, like, typically functions just pass like arguments of a fixed size, but printf allows you to pass variable number of arguments, and they are different sizes. But let's not get into this variable arguments convention. But okay, these guys are sitting on a stack. You jump to the printf function. Printf function goes to a standard library, like you said, standard library, and in x86 it's very simple. So what is happening in x86? We have an interrupt with a number of whatever x40, and how do you pass the fact that you're trying to invoke printf in a kernel? Do you remember? Is it on the stack? I think so. I think it's EAX. So you move some number into EAX. I don't know what the number for printf, let's say 5, right? And at this point, you trigger the interrupt transition. So essentially you say, look, I got it. So I go through the interrupt descriptor table, IDT. IDT will have a, for this vector x40, will have a address of a handler, which will be in our case vector vector 40 or 64. And then we start saving the stuff, right? But we also have to be clear that we switch from this stack. So it's user level stack. We switch to a different stack, which is a kernel stack. And we did it because we don't really trust the user, because this ESP value can be pointing to anywhere, to some unmapped page. And even when the hardware will start saving something on this kernel stack, like saving these 5 things which are saved when the interrupt transition happens, do we remember those 5 things? Anyone can we name the 5 things which are saved? I mean, the logic here is that remember that those are the things which are immediately changed, like as we transition. Like, what are those? Stack pointer, stack segment, E flags, because interrupt transition can disable interrupts, code segment, and what else? EAP, instruction pointer. Yes, because we were sitting here, that was our old EAP, and it changed. We had this stack and it changed. Of course, segments changed along with them potentially, and the E flags could change because if we have a setting here to disable further interrupts, it may disable interrupts, right? Okay, cool. We got to this vector 64, and essentially vectors, like, what are we doing here? Like the moment we get into the kernel, what are we doing there? Well, before getting the arguments, like at a high level, yeah, go ahead. Well, here we're just pushing the number. Here we're just pushing the number 64 on a stack to remember that we're in the 64 system call or 64 interrupt. And all traps, conceptually, like, don't think about the details, but conceptually what you want to do, your main goal is at some point come back to this execution within the process, right? Because maybe it was a timer interrupt, maybe it wasn't even like a system call. And in order to come back, obviously, you need to save the state, because, and you have to save everything. And that's why here in low-level assembly, before even fetching the arguments or anything, you really need to save all the state. So you save, and you don't know what it was, right? So there's 5 things are saved by the hardware, so you don't have to save those. But everything else, like state of the general registers, EAX, EDX, and so on, state of the segments, you have to save in this all traps handler, right? Okay, and it's like, despite the fact that I'm talking about x86, Linux does about the same. So it's a little different because Linux can process like non-maskable interrupts and stuff like that. So this logic gets complicated. Like it takes you like a week to understand what Linux is doing, really, even if you know what's supposed to happen, maybe even longer than a week. But yeah, it's like, but conceptually, it's all the same. Like we are saving the state, right? And the moment we got to all traps, we formed something what is called the trap frame. Let me change the color here. And it sits here on this kernel stack trap frame, right? and we jump to the trap function with the pointer to the trap frame as an argument. So it will be like sitting at the very top of the stack, a pointer to the previous line on the stack, right? And after that, we're in C, we're in the kernel. What dramatic change which happened was we moved from PL3 to PL0. Inside PL0, we can access the hardware, change the page tables, change the global descriptor table, do anything we want, because not all instructions can be executed in PL3. I said that we can access the hardware in PL0. In practice, you can set up things in such a manner that you can access hardware from PL3. And this is the idea is called user level device drivers. Like you will see it later in life. It's just for performance, to essentially to avoid the overhead of system calls. Some super efficient device drivers like network interfaces, NVMe, so like PCIe attached flash devices and probably graphic interfaces have this kernel bypass and they access hardware directly from user level. But okay, got it. So we're inside the trap. We dispatch on a table of possible syscalls because we passed the number, this is call number 5. Like essentially we will go into this printf actually internally. Will be okay, so I skipped a little here. I apologize for that. So printf is a little bit more complicated than just invoking a syscall. What do we need to do inside printf? Like for real, when it's a real example, not my toy example. Maybe it says something like printf a number and you pass a number I or whatever. So printf is actually a useful function in your standard library. So it will parse this format string, right? And it will like do all the conversions. So essentially printf, if you pass a floating point number and you say print up to this number of elements after the dot, it will be like doing all this logic. And essentially, actually, I apologize, but internally printf, after doing all these conversions, it will convert it into a write system call, because write just will be, it's plain data, you pass a buffer, and printf will prepare this buffer. And essentially, when we get to the trap and get to the syscall, you will actually be executing a write system call. And this write up into a specific file descriptor. For printf, you don't even have to mention the file descriptor, it goes to the standard output. And so you will look up this file descriptor in the table of your file descriptors in a process. This will point to, like in a normal case, it will point to a file. And I actually never explained what happens when it points to something different. So it actually, in case of a printf, it points to something what is called a device. And it's a console, and it will or serial line, it will have methods to implement read and write. But at this point, instead of going to a file system, those methods which implement write to a console, in a way similar, like typically in x86, there will be two different things which will be implemented. It will be writing to a VGA console. So essentially when you boot in QEMU, it actually, like if you're doing you can do a no X mode, and it means that it just goes to serial line. But if you do an X mode, it will emulate the VGA. So kind of when you were booting into Hello World and writing those characters in a buffer, like one by one, and like internally the logic of the VGA controller like converts every ASCII character into like a collection of pixels on a screen forming hello, right? So those methods of the console driver will implement it. And so in x86, it goes to two things, VGA and serial line, right? And serial line is effectively a port which you can plug in a different computer and read from that port, right? But essentially at this point, you say, look, I did the write to the console, and then you will start returning from the interrupts, like back to the user level. And at some point, you will end up again returning here at user level, next instruction after the int. And then you will do a read instruction here. A read will return to the next line after this call, right? Which is like next line after the printf. And I mean, despite the fact that, again, we just talked about x86, Linux implements this in a similar manner. So it's like x86 is not too far off. Any questions about this?
So when we call the write function, or write system call from the kernel, is it going to invoke the int instruction again for the interrupt, or is it going to skip that step?
Good question. So what are you asking? Let me rephrase for everyone. So you're saying, hold on, I've seen some printfs here in the kernel, right? That's what you're asking. Or
yeah, but I was specifically asking about what we call the write system call.
In a kernel, from inside privilege,
Yeah,
from inside the printf, from here.
so we call the printf, it switches to the kernel.
No, I made a mistake here. So it doesn't switch into, like, printf will be a library function which will parse the format string and maybe invoke one or multiple write system calls. Every time you invoke a write system call, it will be, again, part of this util library that will invoke int and drop into the kernel once.
So it's going to be the write.
Yeah. Yeah. Inside the write system call, yeah. And printf, again, just because of complex logic of like format conversion, like from floating point integers to whatever, then you invoke write once or multiple times. I don't like you should take a look. It's not very hard to look it up. Let me quickly again. So I keep this anecdotal thing is that, remember I said that I had a student who was who did this very well in this class, and during the exam they were just sitting and reading the source code, right? And if I grab here for printf inside x86 source code, I will quickly like it should be at user level, so I have to figure out where is the utils or something. Printf this. So what it does internally, this is the logic of this formatting. So essentially it says, okay, I figured out percentage, then a number, then I can print a number and print int, for example, here. And like internally, actually, it does the put C. So it puts a characters, one character in the console. So it looks like it will be executing individual put C, like put C calls. And if we grab for put C, we will quickly figure out what it does. That's inside the kernel. Let's take a look here. What is really put C? Looks like this one. So it uses the write system call, but with one character. It just passes one character, one byte into the kernel. So it will, yeah, it's kind of like, it will waste you a lot of time, but it will invoke hundreds of system calls underneath in x86. Maybe there are some optimizations on Linux. Okay, makes sense. Any other questions? So we still have a couple of minutes, but I'm not going to torture you. So this is one useful kind of line of reasoning about what's going on in x86. Hopefully on Tuesday we'll get back to this, and maybe we'll discuss a little bit, because this is kind of from the view of one process. I wanted to talk about how multiple processes are running and what kind of scheduling things can happen. So, okay, sure. So then let's see each other on Tuesday, and then we'll start preparing for the final exam, which is again roughly in about, what is it, in a week after that. Thank you, guys.